Okay, this is Jack Jackson. We're back again with the College Algebra Practice Test 4B. We did the first 13 questions in the previous video, and now we're going to finish them up here, starting with question number 14. So, carbon dating. The amount of carbon-14 present in animal bones after 2 years is given by this formula here. It's an exponential thing. It's lost 18% of its carbon-14. How old is the bone? Again, we have this basic formula that the log of the percentage remaining is k times the amount of time. And so if we want to solve this for the time, that's the log of p over k. Well, in our particular case, it's lost 18%, so the percent remaining is 1 minus that, which would be 82%, okay, or 0.82 is the percentage remaining. Remember, p is the percentage present in a decimal form, not how much you lost or gained. K is negative 0.00012, and just plug this in the calculator and this will work out. This is in years, so 1653.757823, or about 1,654 years. Okay, you could also do it by just starting back at the formula and working with that. You have you'd have 0.82 times the original p0 is p0 e to the negative 0.00012t. First thing, divide by p0 on both sides. That cancels out. So you have 0.82 equals e to the negative 0.00012t. Take the logarithm of both sides, or rewrite it as a natural logarithm. And now it's just like what we did before. Okay, and that's where we started basically before. Now, or if you want, once you get to this point right here, let this one be y2 and this one be y1, or vice versa, and do a calc intersect. That'll also get you the same thing. Next question. The sales of a product have declined in recent years. There were 202 million sold in 1984 and 1.4 million sold in 1994. Assume the sales are decreasing, exponential decay, and we're going to use e to the minus kt. Notice k, what I would just said e to the kt and call k negative because it's decreasing. In this case, they've already factored the negative out, and their k will be positive. Okay, but remember, we can find the base of an exponential by doing the formula y2 over y1 to the power 1 over delta x. Well, let's see what that gives us in this case. The second y is 1.4 million, and the first y is 202 million. Of course, luckily the millions just cancel out. And delta x is 1994 minus 1984. So this is 1/10 here. So we can use this to figure out the base. 1.4 divided by 202 to the power, parentheses, 1/10. And I'm going to store that as b in our calculator. So there's the base. Of course, if you do that minus 1, this is the r. Negative 39.2%, roughly. But they want it in terms of k. So remember that k is the natural logarithm of the base. So if we just do natural logarithm of alpha b, and let's store that as r, No, it's not R. It's K. Stored as K. Negative 0.4971795461, or about negative 49.7%. Okay, so now they have the negative already worked in, so because the negative was already built in the formula up here, then the K would be this without it. So 6 places, 497180. So rounds up 1. Okay. Find the value of K. Estimate the sales in 2002. Okay. So we can use a couple of different ways we could do it. We could do y equals y sub 0 e to the kt. If t is the number of years since 1984, then this is 202. And then put that k, negative 0.4971795461 t. Okay, or we can replace this, if you'd rather, replace t by t minus 1980 if you want to, 1984, if you want to figure out the, want to be able to actually plug in the year number. So either way, you're going to have to take the year number 2000 and the first 2002, and the first thing we're going to do is we're going to subtract 1984 to see how many years have elapsed, and essentially this becomes our exponent, 18. Well, it becomes the t part here, so it's 18k. Now I stored k with a negative, so then the amount in 2002 is going to be 202 million. Okay, 202 million times e to the power. Well, you know what? Let's go ahead and put millions. 202, and then it should be 202 thousands, millions actually. So let's go ahead and do that. 202, 1, 2, 3 zeros, and then 3 more. 6 zeros all together at the end. 1, 2, 3, 4, 5. I think I put an extra one. 3, 6. Okay, so that's 202 million times e to the power. We'll use our alpha k, and then we'll say times, what do we work out? 18 for the elapsed time, and this should tell us 26,227. Round off the nearest whole number, which is what they have here. In what year will only 1% of the product be sold? When will it get down to, only one of the product sold? So you want this to be, you want to put y equals 1. So 1, if this would continue long enough, I'm just going to say kt with my k that I have. And so we want to divide. That's e to the kt. We're solving for t. We do a logarithm. And that's kt. And so t is, well, that divided by k. That gets rid of the k. So it's natural log 1 divided by 202 million. 1, 2, 3, 4, 5, 6. Okay, that's right. And then divide by our value of k, alpha k, and that's the time, and it is approximately 38 years, and we want to need to add that to 2000 or 1984, excuse me. so about 2022. So if this would continue on at this rate, that would be down to only one of the product being sold in 2022. There's a good chance that this model will not hold that long, that this is a short-term model. It's only good for several years. So we're probably extrapolating out too far in the future for this model to be actually accurate. But if it were accurate, that's what you would get. Next question. Okay, a coin sold for $286 in 1975 was sold again in 1988 for $469. Assume the growth was exponential. I think we did one like this earlier already. We have the value, two x's and two ordered pairs of xy, and so we can use that to find the base if it's exponential. Remember, it's y2 over y1 to the power 1 over delta x. So y2 is 469, y1 is 286, and it's 1 over, so it would be 1988 minus 1975. That's 11 years, so I'm just going to do that in my head, 1/11. That fraction might be able to be reduced, but I'm just going to leave it like that and not worry about it. So 469 divided by 286 to the power 1/11. Don't forget parentheses around that power. And this is my base. So I'm just going to store it as b in case I need it again later. Okay. Now, so one version of the formula is initial amount 286 times b to this b to the power x, or t, where t is the years since 1975. I believe that's what they wanted it set up. Look here in part B, t is going to be the years since 1975. However, they wanted it in terms of k. So remember, k is the natural logarithm of b. So I just do natural logarithm of our previous answer there, and I'm going to store that as k. Okay. Now, if I they got a different value. Let's make sure I don't have a typo here. 469 divided by 286. Oh, it's not 11 years. It's 13 years. So that's a 1/13. Let's start over again. So 486, no, 469, get it right here. 469 divided by 286 to the power 1/13. Okay, there we go. So we take that and store it as b, and then take the logarithm of the b and store it as k. Okay, that agrees with their answer, 0.038. Now, if I remember doing this problem earlier, they used the rounded off version, like they shouldn't have, to do the rest of the problem. So I'm going to use the rounded off version so I can match their answers. And the equation is right here. It's the initial amount, 286, e to the k, t, and the k was 0.038. And we're going to use that rounded off version to do the rest of our problem. I'm going to go ahead and type that in. Like that for it. And let's choose an appropriate window for, say, time 0. I don't know. This might be good for, we're assuming it's good over the 13 years. Let's go out like 25 years. Or how about 30 years? We'll mark it off in 2s, or how about 5s? And y certainly won't be negative, but let's, we're starting at 286 and then going up. So let's start here, maybe 250, and go up to 1,000, and we'll mark it off in 50s. I said 100 instead of 1,000. That's going to give me an error message. There we go. Let's see what the graph looks like there. Yeah, that's pretty good. That's a good window. Okay, so how much is the value in 2013? Okay, let's make sure I get the year right this time. 2013 minus 1975. I'm looking for an x or t value of 38. So if I go to trace and then type in 38, that'll take me to, oh, that gave me a problem because my window didn't go out to 38. So if I'm going to go out, I should have looked ahead, I guess. I need to go out 38. I need to go out further than 38 here. So let's go out 50 years. If we do that, we might want to go a little higher. Let's go 2000. Okay, now do trace 38 years. There we go. 1,211, 1,212. We round it off to the dollar. Okay. What's the doubling time? Well, a couple of ways I can go at this. I can go here and actually type in double this, so I can type in, 2 times 286 and graph it and just calculate that intersection. So I could do it that way. Calculate 5, enter, and I guess, and I get about 18 point something years, 18.2. Okay, but I can also do it as, remember the ln of p equals kt. So if we want the doubling time, that's ln of 2 and divide by, well, k, what I've got stored is k. This is if we don't, here's if we don't round it off. So here's the x that we just came up with there. If we don't round it off ahead of time, be ln of 2 divided by the k value we came up with. Maybe off a little bit. Still rounds off to 18.2, so that's good. If we did ln of 2 and divided by the k that we have there, 0.038, the rounded off version, notice that one agrees with the x that we got up above, because the x up above uses a rounded off version in the graph. In this case, it didn't make any difference. Found amount of time after which it will be 1,819. We can solve that algebraically, or we can just go to here and type in that y value. I'm going to do it this way. And type in the value, let's see, 1,891. 1,819. There we go. Graph that and find out where these two things cross each other. Oop, just barely fit on the screen. Now if it's off screen I might have to adjust, but I think I can get it from here. Calculate the intersection. Enter, and this is way out there. I'm going to just guess 49. I think our window went to 50 if I remember right. 49 is pretty close. 48.7. Okay. Alright. Let's go on. This is a supply and demand function. Supply is the producer's willingness to supply. Now this is always going to be an increasing function. Okay. And so we're going to have the price. In this version we have the price and here we have the quantity on this axis. And supply always increases. There's going to be some minimum price at which it should probably go something like that, because there's going to be some minimum price at which well, this model's not so good, because if you plug in 0 in this model, it actually crosses at 1, and then it goes up, which says that they'd be willing to supply 1 for free. Yeah, not likely. It's more likely to be shifted down a little bit. But anyway, that's what they've got for a model. The other one starts up here higher at 480, and it's a decreasing exponential, and that's the demand curve. The demand, the quantity, both of these are quantities as a function of price. So let me explain this just a little bit. Supply is the producer's willingness to supply. So the more they can get for the item, the more collectively the producers are willing to supply. Okay? The demand curve is the consumer's willingness to purchase, how much they demand. So the lower the price, the more the demand is going to be. So if they're giving them away, they would demand 480 of them. And then as the price increases, they're going to go down less. This point right here where they cross is called the equilibrium point, or market equilibrium point. Of course, you have some price and some quantity. That's going to be your market equilibrium, and we're looking for the equilibrium price. So we're just wanting to know the x value where these two cross. So let's go ahead and do that. They're both exponentials. One's increasing, one's decreasing. 150 e to the power 0.004x. That's the increasing one. That's the supply curve, and the demand curve, 480 e to the power negative 0.002x. That's a decreasing one, so that's the demand curve. This is a first quadrant graph only, so we can start x at 0 and start y at 0. And the y is going to start up here at 480 and come down, so we might as well take the max to be around 480. I'll just make a nice number. We'll make 500 on it. Maybe mark it off in 50s. That's fine. Or, yeah, 50s is fine. And I don't know how far out we need to go here, so this is a little bit of a question mark. But let's try 100 and mark it off in tens, and this may or may not be a good window. So let's graph that and see what we see. Okay, the intersection point is definitely off screen. 100 doesn't look like it's nearly far enough. Maybe we need to go 200 or 300. Let's try 300. I'll mark it off in 50s as well. Alright, I think this looks a little more like it. Yeah, you can see that intersection point quite nicely now. So now let's do a calc intersect. Enter first curve, enter second curve, and put as close as we can to that intersection. The market equilibrium point is now about $193.86. This is actually, when I say price, it's really unit price. So that's dollars per item. That's what that really is. $193.86 per item. That's what we're looking for. And when you do that, there will be 326 items sold. Following the birth of a child, the parent wants to make an initial investment of P sub 0 that will grow to $50,000 for the child's education at age 17. Interest is compounded continuously, so that's y equals y sub 0 e to the kt, or A equals PECT, like that. Okay, and it's compounded continuously at 5%, so K is 0.05. The initial investment is P0, or just P. That's what we're looking for. And we want it to be $50,000, actually when T is, this should be in years, 17 years. Okay, so just solve for P0. So that's P0 is 50,000 divided by e to the 0.05 times 17. Okay. 50,000, sure I got the right number of zeros, divided by e to the power 0.05 times 17 years later. And this will be what we need to put in the bank to begin with. Right there, $21,370.75. Not bad. If we can put that in and we're guaranteed that rate for the entire 17 years, like a 17-year CD or something, okay, compounded continuously, then that's how much we need to start with, and we'll end up with $50,000 17 years later. Alright, 19. Well, if this is this a geometric sequence? Remember, geometric is just another name for exponential, basically. So we want to see if there's what if the base or common ratio is the same. So negative 3 over negative 1 is 3. Negative 9 over negative 3 is 3. Negative 27 over negative 9 is 3. It does have a common ratio, so we do have a base of 3. Okay? So that's good. And we know the formula then is the nth term, well, it's like y is y sub 0, b to the x. So changing letters to what we usually use for sequences, it's the 0th term times b to the n. Well, the 0th term, we could do it that way, or you could do it as the first term, and then we do n minus 1. So we could do either way. To do this one, we have to figure out what the 0th term would be by backing up, dividing by 3. So this would be negative 1/3, negative 1/3, and then we'd have 3 to the n. Or we could use this version and just do the first one, negative 1, and then we could have 3 to the n minus 1. Either way, it'll give you the same thing. So if we want to find the 9th term, it's negative 1 times 3 to the 9 minus 1 is 8. So it's negative 3 to the 8th. Alright, well, let's see what's 3 to the 8th. 6,561, but it's negative. And you get the same thing up here if you did 3 to the, and actually put in 9, and then times a negative 1/3, you get the same thing. It's negative either way. Find the general term. Well, if you look, this one is just alternating signs, so the common ratio is negative 1, and the first term is 5. So the nth term is 5 times negative 1 to the n minus 1 would be the appropriate one. So it's first term. It's basically this formula right here again, where we know the first term is 5 this time, the base is negative 1, and we get that. And of course you could just check it out. If you plug in n is 1, you get a power 0, and negative 1, 0 is 1, times 5 is 5. Put in 2, you get negative 2 minus 1 is 1, so you get negative 1 of 1 is negative 1, times 5 is negative 5, and so forth. Alright, this one's dealing with the sum of a geometric series. So first of all, let's make sure we see that it is geometric. 12 divided by 6 is 2. 24 divided by 12 is also 2. So the base is 2. The common ratio is 2. Okay, and what is the sum? Okay, the sum of a geometric series is your first term, 1 minus base to the number of terms over 1 minus the base. A lot of books will use R here for common ratio, but I reserve R for the percentage rate of growth. Okay, so A1, the first term is 6, the base is 2, and the number of terms was 7. Now, by the way, this can also be written when you have a base bigger than 1. It's sometimes useful to write it this way: multiply top and bottom by -1. You can also write it that way. So, in other words, I could do 2 minus 1 here, and 2 to the 7th minus 1 here. 2 minus 1 is 1, so this is 6 times 2 to the 7th minus 1. Okay. $762, which is exactly what they have. Alright, we have to determine if this is geometric or not. 5, -5 times the square root of 5, -25, -25 square root of 5, 125. Of course, you could always make a geometric with 2 terms, right, or 2 points, but what about 3 or 4 or 5? They may or may not all be geometric. What does it take? That base has to be constant. So -5 divided by -5 square root of 5 over 5 is negative square root of 5. Alright, -25 over -5 square root of 5. Alright, this is a little harder. Let's see, I need to multiply top and bottom by square root of 5. Okay, square root of 5 times 5, square root of 5 is 5, times -5 is -25. That cancels, and you get, looks like that's positive square root of 5. So it looks like we're already out of luck. -25 square root of 5 over -25, that's positive square root of 5. Did I miss a negative here? No. No, I did not. So that one works out to be square root of 5. And the last one, 125 over -25 square root of 5, multiplied by square root of 5 in the top and bottom. This is negative square root of 5. So if it wasn't for the signs, we would be geometric, but without the but the signs are messing things up, right? So if it would either all be positive or all negative or alternate, it would have worked out. But this positive, negative, 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 positive thing threw it out of whack. The square root of 5 part was fine, but these have to be the same, and they're not. So it's not geometric, not exponential. Alright, the next one we're adding up, k equals 1 to 4, 54 times 1/3 to the k. Now there's only 4 terms here. We could actually just figure out all 4 terms and actually add them up. Okay? But notice that this is the form of an exponential function. If you plug in k as 1, well, anyway, this is the sum then is a1, 1 minus b to the n over 1 minus b. The first term is when you plug in the lowest number here for k, so it's 55 times 1/3. That's the first term. And then this is 1 minus the base of 1/3 to there are 4 terms, top number minus bottom number plus 1, or just 1 to 4, it'll be the top number, 4. And this is 1 minus 1/3 here. Okay, well, let's clean this up a bit. Well, just type it in the calculator. 55 times 1/3 times parentheses, open parentheses, 1 minus, open parentheses, 1/3, close parentheses to the power 4, close numerator, divide by, open denominator, 1 minus 1/3, close the 1/3, close the denominator, close the whole fraction. Boom. Oh, I copied it wrong. I said 55. It should have been 54. Let's change that. Should have been 54. Everything else is right. So let's change that. Let's go second entry. And that should have been a 54. $26.6 repeating. So they wanted it a mixed number for some reason. I wonder why. It's 26.6 repeating is exact. In a fraction form, that's 80/3, or it is 26. So subtract the 26 and we get the 0.6 repeating, or 2/3. Well, there it is, 2/3. 26 and plus 2/3 or more, 26 and 2/3. Or if we've gotten the 0.6 repeating, we could have changed that part to a fraction. For some reason they wanted a mixed number there. Alright, now this one is, the formula is a little more complicated for this one. This is an annuity. To create a college fund, a parent makes a sequence of 18 deposits of $1,400 each, in a savings account on which the interest is compounded annually at 3.8%. Find the amount of the annuity. Okay, well, let's do it out sort of the longer way first. So they first make a $1,400 deposit. So that's after one deposit. After the second year, they've got that $1,400 and it's earning compounded annually at 3.8%. So we're getting 1.038 will be the amount plus another $1,400. Okay, let's clean that. Let's factor out the 1,400, and that's 1.038 plus 1. Now A3, we take that amount, multiply by 1.038. At 1.038 is our base because of compound interest. And then we're going to add our another deposit. Okay. Distribute here. So we're going to distribute this and this. So it's 1,400 times 1.038 square plus 1,400 times 1.038 plus 1,400. Or actually, let's leave the 1,400 out. That's 1.038 square plus 1.038 plus 1. This is starting to get a pattern here. A4, we take that amount, multiply by another 1.038 and add 1,400. Again, we can factor out the 1,400 and we're left with, when we distribute here, 1.038 cubed plus 1.038 square plus 1.038 plus 1. By the way, 1 is 1.038 to the 0. So this is the sum from k equals 0 to 4 minus 1, 1.038 to the k. So in general, we can generalize this. After n payments, n deposits, it's 1,400. 1,400. Right, 1,400? Yeah. Times the sum from k equals 0 to n minus 1, 1.038 to the k. Or put this inside, it doesn't matter. Actually put that inside here. So what happens is, this is a geometric series. Okay, so we know it's a1, 1 minus base to the n over 1 minus base. Or if I'd rather a1 base to the n minus 1 over base minus 1. I'd rather use that because it's a base bigger than 1. So, the first year, when k is 0, okay, is just 1400. The base is 1.038, and we want to raise that to n payments minus 1. 1.038 minus 1. So the bottom is just 0.038. Well, let me do it this way. 1400 divided by 0.038, and this is 1.038 to the n, and then minus 1. So that's the amount after n payments. Okay, how many years are we going to do it? 18 payments. So just plug in n as 18. Let's do it on a calculator. 1400 divided by 0.038, 1.038 to the power of 1400. No, not 1400. How many years? 18. Just the power 18. Minus 1. There we go. $35,251.51. Yep, same thing. Okay, I want to try something. I think there's a short time value of money solver. Put in the number of payments here, 18. Put in the interest rate here, 3.8. The present value at the beginning is 0. The payment is coming out of your pocket, so it's negative 1400. We don't know the future value yet. Payments per year and conversions per year is 1 at the end of each unit. We want to solve for that future value. Then do alpha and enter, which is solve. And notice that it turns out to be that future value, 35251.51. This is also very useful for figuring out mortgage payments. In a mortgage payment, you would start with a certain amount of money and the future value would be 0. Here we go. We can let's see. Roberto borrows $13,000, loans to be repaid in 7 years at 7% interest compounded annually. We made him one payment at the end. So this is not an annuity payment. This is all at once. So compounded annually. So this is basically our y equals y sub 0, 1 plus r to the x kind of formula. So the amount owed is the amount borrowed, the principal, 1 plus the rate to the time. But we got to do this, it's compounded annually, so time is in years and the rate's per year. The rate is 0.07. The number of years is 7. The principal is 13,000, and then that will give you our amount. $13,000, 1 plus 0.07 to the power 7. And this is how much he has to pay at the end. $20,000 $875.16, which is what they have there. Now, what if I think that's the end of the test, okay? But what if instead he was to pay this in payments? Then you can go and use this Tvm Solver, just to show you how this works again. So, it's done at 7% interest. Let's say it's 7% compounded monthly this time instead of annually. So, we put in 7, not 0.07, but 7. He's going to borrow $13,000. In the future, it's going to be 0, because he's going to pay it off. 12 payments a year, which is 12 conversions a year. It's going to make 12 payments, and it's figured out interest 12 times a year. But we want to figure out what his payment's going to be. So that's the one we're missing. And so we notice it's negative because it's coming out of his pocket. So if he borrows $13,000 and makes it off in payments, he'll be paying $726.90 per payment. And of course we could take that times 18 times 7 payments. No. Wait a minute. Let me go back to that. I had it in 18 payments. So definitely not 7 years. Let's say he did 7 years. So it'd be 7 times 12. 84 payments. And let's see what his payment would be. A lot less. $196.20 per payment. But he's going to do that for 7 years. So how much did he pay altogether that way? $196.20 times 84 payments. He was out this much. Which is actually a little less because he's making, he's not paying it all off at the end. He's paying some of it as he goes. But notice how the calculator can figure that out. That's going to be pretty useful to you if you have to figure out, say car payments, for example. Okay, I think that wraps us up on this practice test. So enjoy studying that. Practice. Go over this as many times as you need to. And the actual exam will be quite a bit shorter, but very similar to what you see here in these videos for the types of questions. They'll probably be some of the same questions again. Of course, they're algorithmically generated, so you'll get new numbers each time. But this is probably about what you can expect for the actual exam. Just shorter.